Sorry for the trouble. So, thanks for staying back. And yeah, myself, I'm Ashok. I'm staff engineer at Apple, and I'm going to talk about zero trust architecture on how you can build agents. So, recently, in the past 2 years, agents have been like a buzz. Obviously, everyone's like started to build agents. But there is a lot of accountability goes into building agents because you're kind of giving access to the entire platform, memory, databases, whatnot, right? So just give every little access to the agents. Now, obviously, everyone wants to churn production code faster, take applications features out faster. So that's kind of the most of the reason why you kind of go build agents faster. So the idea is like, how do you build responsible agents? Like essentially the core of responsible AI, understanding how, what kind of trust factors you should understand while you're building agents, what guardrails you need to keep in place, how you essentially like structure the whole thing. There are obviously like just gentlemen spoke about the agent code platform, which was explaining about. So it gives you fundamentals of how you can build an agent. Obviously, you can also use open source fundamentals. So here I'm going to go talk about a lot of open source fundamentals on like what you can do, and at the same time conceptual, grounding of like how you can confidentially build agents and make it more responsible. So we get into it. Essentially, the landscape of this whole entire architecture, I kind of try to explain it with a simple example, like an email, for example, right? So everyone would have heard about like SQL injection, similar to that, like the prompt injection is something also is like becoming a kind of a threat right now. Taking this as an example, if someone just comes up and says, like, as part of that email, let's say you're processing the email, and in that they kind of inject certain prompt to override the system to take over. That's one simple example of how it happens, but it's not always simple in scenarios. There are different type of examples where things can go wrong. So understanding, how that prompt injection would work is what this is highlighting, right? So it knows the context, it embeds the text and finds the information in the vector DB, and whatever it needs to process, it gives you back that information. So this whole process actually has no guardrails, no responsible AI in it, essentially no governing platform. So it misses like a lot of things which it should ideally have. So the overall, like, how do you want to govern agents? How do you want to make it responsible? Is split by like these 5 different modes of architecture. Essentially, having workload identity. I'll explain like how you can add a workload identity to an agent or an AI system, and policy engine, a durable execution where you can actually understand what an agent is doing, how long it's working, how to make it stateful. Vector store, obviously the memory portion of it, where long-term, short-term came into picture, which we just heard about. Confidential enclave. Actually, confidential enclave is a term which a lot of people are understood as confidential computing in the past, but a confidential enclave is actually even more important in terms of agent code when you want to build the agents. I'll explain what is confidential enclave when you want to build agents, how it's done when you're building your own agents. Most of the time, cloud providers provide you this, and you would not have to go and understand or learn about this. For example, like Amazon, Google, these cloud providers would provide you this confidential enclave, so it kind of comes part of the systems. But when you go open source, when you build it and you want to productionize it, and you don't use other cloud providers, instead you would want to build your own open source platform, you need to consider confidential enclave for your own purposes to safeguard your agents. So what's workload identity, right? So typically in API-based systems, you know that you get security tokens, API tokens. For example, if you want to use LLMs right now, you get these tokens. There have been scenarios where your tokens being used by someone else, and someone else got charged for it, whatever, right? Whatnot, it happens. And I know I gave my token to someone. Fortunately, I had a cap on it, like $10, and they didn't use more than $10. So things like that, with the token, obviously it can get exposed. So short-term live, basically the TTL of particular tokens is something you have to keep setting. It's just not an easier way to work with. So for agents, how you really do work with it, right? So basically, instead of using static API keys, you can use something called basically Spire, which is a secure production identity runtime environment. So the Spire is a framework which you can actually inject into the agent, and you can have a Spire server. I'll explain and go into the architecture next. So the agent will have the Spire agent as a sidecar agent all along, so that it can generate its own workload identity. So the workload identity will always gets generated for the agent at a particular agent level. So every single agent you are actually running will always have workload identities, which will contact to the server. This way, every agent is kind of considered to be its own, agentic workload, and only if it's identified, it knows that you are in a secure environment. So you're not actually sharing like static keys and an API level keys into the agent. Instead, they work as a workload itself. Now, how that really works is basically handshake and acknowledge, right? So here you can see the agent process. So agent process starts, it goes and kicks into the Spire agent. The Spire agent will basically create a workload identity principal, and then it will give you a certificate back. Certificate has a time to live, and then it actually then go try to contact the DB, memory, vector store, whatnot in other parts of the world of your system. And the same token and the same certificates are also shared to other systems, so they know that this is authenticated and this is acknowledged information, and that's when the memory is exposed. So doing this is pretty critical, and this is probably the most fundamental thing you can do to build an agent. And if you miss to do this, obviously there is a potential leak of memory. You don't know who's accessing what data, and the agent basically can just go rogue and access any data, which it shouldn't really be. I used to be also working on some of the healthcare related work, where like patient information and personal information used to be guarded, and it's considered like very safe and secure. Obviously, privacy related environments, it has to be considered important. Government related information also, it has to be considered very important. So this particular architecture is an evolving architecture, and this is what I'm seeing used by a lot of, I would say, top of the line companies like Netflix, Uber uses it, Palantir. So a couple of companies basically have architected this, and each have their own version of namings for it, but this is the actual open source architecture behind it. So we spoke about the workload identity, so I would like to move towards something called governance. Essentially, once you did do a workload identity, you know that this is secure. How do you know that the information which is being asked or requested of is the right information, right? Is actually credible information. For example, you can go to ChatGPT right now and ask for like, do this, but obviously it doesn't want to do that because it's malicious. So you want to understand the malicious intent of the particular request, right? So the difference is that you don't want to use LLMs or the specific agents itself to understand the maliciousness, because they are not deterministic. So you want to add a deterministic logic to the particular platform. So that's where this OPA comes into picture, which is actually Open Policy Agent. So the Open Policy Agent kind of runs a policy engine and makes things deterministic, and you can actually do this using small language models. So the SLMs are typically used for this purpose, where you can run an agent level small language model which runs within, takes these policy engines, and then these policy engines are updated in runtime, and you can basically inject a policy at runtime if you want, and the OPA will take it in, and that OPA will always run as part of the agent. So agent will know exactly what it is doing, so that the cost of your the latency of your agent's policies and guardrails are much shorter. So this is kind of an evolving architecture as well, but instead of using a guardrail service, which is like outside of your system, using it within the agent has been a practice which I'm seeing coming along these days. So the policy logic kind of looks like this, as simple as like, okay, if I do a get, this is the level of data level clearance you need to have, how long their token should have expiry and all that. So you can actually keep increasing up to the level of information you want it to be. Some of the examples I've seen is like someone is trying to book, let's say, 100 flights for like 1,000 customers. Shouldn't be allowed, right? So you just say no. You shouldn't do that. Just because the agent has the capability to go do that, because it can call all the APIs to do it, you shouldn't allow it. So the policies will basically safeguard you from doing that. So the durable execution is basically the third pillar of governance. And the zero trust architecture is basically, how do you ensure that the agent basically is durable at the same time it's resilient, and you can trust it. So agents running, suddenly it crashes, right? So Once it crashes, like how do you bring it back again? Yes, there is long-term memory, there is short-term memory, as we all understand. But the problem is that actually, is it stateful? What state was it running in? Where did it stop? What should I do next? There is too many different things which needs to be handled, which is actually where the durable concept comes into place. And this is actually particularly handled in Uber through a product called Cadence, and basically in open source they call it Temporal. So Temporal is a good platform actually, basically, where you can build durable concepts. And also I've seen people do it with Celery and a couple of other open source products where you can actually build durable workflows with state machines, with inbuilt databases where it comes along with it, like Postgres, things like that. So you actually can build durable agents using that. So anytime a particular agent's running, it knows its memory state, it knows its session state, it should know its guardrail state, and it will basically get stored into a particular into some sort of a memory layer within that durable concept. And if the agent crashes, it'll be able to kind of pick everything back up again. And it does find out, let's say the identity is compromised or the identity is expired, then what happens is it immediately goes to the sidecar agent Spire. It'll give a new workload principal, and a new workload principal will be used to again, reinstate the whole state again. So it should be, as automatic and as quick as that, instead of having to use the same workload principal again. So all of this needs to be embedded within the duration platform. So what is confidential computing? So that is actually something I'm very fascinated about, because everyone have seen this Skynet kind of things happen, right? So obviously in future, as you keep evolving in the space of AI agents, people are like, open up all my system, let the agents do everything on its own, automate as much as you can, right? So that's where confidential computing comes into place. Yes, you can automate, don't stop automation, but there is a way and things you need to do at a hardware layer, which a confidential computing will provide. Essentially, the trusted environments, what it actually gives you is, from a chip layer, it basically gives you an encryption method on how what should be accessed. Basically, an agent, when you open it to the agent OS, it actually can access all of the agent OS, the particular operating system's capabilities of hosting something. You can say, okay, I'll put it in a Kubernetes pod, and the pod will only have access to a certain environment. But it still can do a pseudo level access on something which you shouldn't really want to do. For example, someone can inject into your agent saying, this is what I want you to do. Instead of doing the actual agent's work, it can just basically go and delete files on your system. It shouldn't be doing that. So what happens with the confidential computing is you basically create an enclave environment. The enclave environment is, one such enclave is Intel SGX, which actually is provided by Intel. NVIDIA provides an H100's Grace Hopper, where they give you an enclave on the hardware, which basically is an encrypted message on the chip. So a CPU, when it tries to go contact with the GPU, when the memory is shared, this enclave chip only can contact with this particular GPU, because that encrypted information is come through this chip. So that's an enclave which gets created. Now the agent can only run within that enclave. It cannot go over that enclave. So you basically create this invisible isolated boundary. That way the agent's kind of settled within that, so it cannot actually go access anything else outside of that system other than what it is allowed to do, because only you will give that particular bits of encrypted code to that agent where you want it to work through. It will not have the same code will not work everywhere else. So that's how you actually can contain the agent and do the work only within that particular enclave. So you can actually read a lot about it. There is a concept. Obviously, there are something called libOS, the library OS, which you can find through the open source methods from Gramine and Oculum. It gives you Gramine gives you this library OS which you can install on your agent. Once you install on your agent, it knows the particular hardware you're running the agent on, and it will be able to generate the keys which only the GPU or the inference or whichever system will understand. So that's how you can create this enclave environment. Essentially, you put everything together. There's still one piece of puzzle which is missing here. Essentially, what that is like, let's say you do get some information like I'm someone with, let's say, some sort of a diabetes or heart condition, and I say, hey, help me out in doing this. Now you're using vector database, which is keep storing whatever someone is giving me a request, or third-party systems where, let's say, you're using someone else's models, right? And you keep asking those models, hey, answer for this particular request, but but that request has very specific privacy information, and you don't want to expose that, so you want to redact it. So essentially, redaction is part of the protocol here. So ensure that the information you are putting into your vector store, as well as third party, is redacted, and you don't send any information which shouldn't be sent to anyone else, right? So redaction is an important. That's essentially what here it's called as airlock. So chaos engineering, test, failure scenarios. Ensure you're simulating all the failure scenarios as you can, and store all the historical records, latency checks, compute environments. For example, can I access? I was able to guard it through an enclave, but can I still access the let's say, some other agent's data or some other agent's memory? One such example I remember once we were doing chaos testing was that a patient asked a question and they said, do this. And another patient came up and asked questions about the previous patient, and they were able to get that information. Basically, it was not guarded, right? That's why it happened. And this was again through chaos testing. Hopefully it didn't go to production, but we were able to figure that out, right? So chaos testing is important, and you need to kind of simulate all these different types of systems to understand ensure that it is guarded within the specific. Although it's the same agent, if it is context switching between multiple systems, you ensure that it is guarded and the information is identified and it is not leaked to different parts of the system. So that's chaos engineering would help you cover that. So this is essentially the entire OpenStack of how things are now kind of created, and how do you want to stack it up. So identity, policy, state, isolation, and airlock. So once you put these things into your agent, it becomes responsible agents. It is zero trust agent at that point, essentially. And this I feel is like a very critical component, which right now a lot of systems, teams figure out after they build systems into agents, and then they go into production, and then they come back because the customers yell at them saying this is not working the way, because it's not working for the 5% of the users. 95% of the scenarios it does work, right? Because LLMs are good. But 5% is what is going to take your system whole thing down. And because they're not ready for production, they're not ready for production because they are not having any of these systems in place. So you need to have a governance, responsible systems in place for your agents to go to production, and this will actually make it happen. So yeah, that's kind of all I have. If you have any questions, feel free to ask me. Yeah, I understand. Yeah. So there are two layers of problems in this. One is like the agent itself is trained on certain policies, and second thing is like you're injecting additional rack kind of a memory to the agent where the policy is appended. So in both scenarios, versioning is a problem, and you would need to tackle them. So let's say I'll just concentrate on the how do you inject a rack-based system, right? So it will go like any configuration system where the configurations are managed, and you have a config versioned, and you have to know that the particular SLM model you're using and this version is compatible, and they will be tested together, and evaluation sets are released. Once basically every single guardrail will have its evaluations code. Like that's a semantic evaluation you'll run against them. So once you meet that benchmark, then you start to go into production. Once you go into production, typical versioning will happen where you would release them one by one, and you keep running the evaluation that every single production systems are meeting that benchmark number. If they are not, you stop. And then if they keep meeting, then you continue to do. So typically where it won't meet is when systems are having some sort of a data lock scenarios. where production data comes in, and there is when you go release this, that production data is not compatible with the policies you're injecting. Because of that, your benchmarks are not meeting. Then you stop there, you look at the data, see what's gone wrong, what data. Observability is very important there, where you need to understand where it didn't really go wrong. Then you have to update your policies according to that. So typically, when benchmarks are good, you can automatically keep pushing it. Any other questions? So the highest latency which we have seen at least mostly the guardrail portion of it. Because the enclave is hardware centric, it would directly be able to run directly on the hardware. The encryption keys are created at like every 1 hour, 5 minutes. So the same keys being repeatedly used in a specific window, and the key gets created in like a very less than like a half a millisecond, I would say. But the most points where like guardrail is where it'll go. That's why we were trying to kind of get into like from a service layer into an OPA layer, where you can actually write a SLM agent and then install directly on it. So SLM gives you much faster approach of like 10 milliseconds to a 50 milliseconds in terms of every single request I've seen. But when you go through a service, it becomes like over 200 to a second because of service API latency. So yeah, OPAs are much better way to do it. But the problem again with OPAs is that you have to when you kind of try to go versionize it and take a new model out and you retrain it, it becomes difficult to manage multiple versions of it. So it's essentially that VCS control has been the problem, but that's possible. Once you have like good process, it's typically manageable. So yeah, but these are important pieces, I would say, in terms of like how we want to do it. Maybe they will add 100 to 200 milliseconds in every single request in overall cycle. Which is not a lot. It's better to give the right answer than the wrong answer, by adding 200 milliseconds. Yeah. Can you first point of it? Memory write path, you said. So can you expand that question? Oh, okay. Yeah, that's exactly what I was saying as redaction. You would need to keep doing that, obviously, for auditing purpose, and as well as certain systems have compliant HIPAA and GDPR policies you need to follow. So for auditing, you have to keep writing them. But again, you cannot just write everything outside of a certain environment, right? So for that, there are scenarios where it gets written and then you have a pipeline which gets pushed. And sometimes you have a redaction agent in the same process and you redact the data, then you write it. So before even the data goes into some sort of a persistent store, you ensure that it's redacted. So yes, write is something in regulated, like you said, it has to be there for auditing purposes. Otherwise, you'll have compliance issues. Yeah. Great. Thanks a lot again for the opportunity.